Okay, hello. Today we're going to be talking about the Banach space CAB. So the first thing we're going to start with is defining what is called, definition, the sup norm, which is short for supremum norm, which is that you take a function f, this is a real a function from real numbers to real numbers, and you take the supremum, so the supremum of the set of all the absolute values of x, where x is in the domain of the function. So f is just some function from D to R, and D is just a subset of R. Now notice that because we're taking this absolute value here, that this value here is going to be greater than or equal to 0. And also notice that this is only, quote, useful when f is bounded. In other words, when f is not bounded, then this supremum is going to be infinite, and then you're not really the norm. The sup norm of f is then not going to be a real number, so we're going to be concerned with dealing with bounded functions. The next thing that we can define is what is this C of D, right? This is just the set of continuous functions from some domain, which is a subset of R again, to R. Okay. And in particular, we're going to be studying C of this closed interval AB. So now we proved before that if f is continuous on, say, right, the closed interval a to b, then f is bounded so the sup norm is well defined as a real number. And we get this theorem that for f and g bounded a to b, and alpha is any real number, then three things are true. The first is that the sup norm of f is equal to 0 if and only if, of course I could have shortened this to IFF, but if and only if f of x is equal to 0. I should say identically equal to 0, right? The function f, I'll just get rid of the f of x. I'm just going to write f equals 0, right? F is always equal to 0, at least on the domain a to b that we're considering. The next is that if we take the sup norm of alpha times f, right, which is just the function that you get by multiplying every value of f by alpha, this is going to equal the absolute value of alpha times the supremum norm of f. The third outcome is that if we take the subnorm of f plus g, this is going to be bounded by the sum of the supremum norms of f and g. And so, in a way, this is like a triangle inequality. And really what these three things say is that this sup norm is a well-defined norm, right? So there is such a thing as just an abstract norm on a vector space. And the norm has to satisfy these three properties, and if you notice, like, this is similar, these rules are sort of similar to that of a metric space, and you can actually use a norm to define a metric. And so I say this as a theorem. I'm not going to prove it. The first two claims are very simple to prove, and the third one, you essentially just use the triangle inequality for real numbers, because f of x plus g of x is the sum of real numbers, so its absolute value is going to be less than or equal to the sum of the absolute values of f of x and g of x separately. And essentially, this side is going to be an upper bound for the set of values of f of x plus g of x. And then the supremum has to be the least upper bound, so it has to be less than or equal to this other upper bound. But I don't want to spend that time writing everything out. So essentially, the idea is that this C of AB is a normed vector space. And normed vector spaces are extremely important in analysis, and really the idea here is to just give a sort of introduction to what normed vector spaces are. Really, I could have skipped this part, but I think it gives a good introduction to what like a graduate course in analysis would look like. So what does this mean, right? So a vector space, you may have seen a vector space before, and I plan on covering this in the algebra lectures, which in hindsight, I guess I should have done beforehand, because I defined the real numbers as a field, and now this is a vector space. And so really a vector space is just a set with certain certain properties it has to obey. And I should specify this is a normed vector space over R. Right? A vector space has to have an associated field. We know the real numbers are a field. And so essentially the key ingredients in a vector space are a zero, right? So I guess you could define a zero function to just be equal to 0 everywhere. If f and g are in the space, then the sum is in the space, and alpha times f, if alpha is a real number, then alpha times f is also in this space. And these are basic properties of continuous functions. this is nothing new. We're just sort of we can simply state it in this one sentence, right? That C of AB is a, well, the normed vector space part. So this is just saying that it's a vector space. So vector space, and then there's other additional properties, like addition is commutative, and so on, right? But now the fact that it is a normed vector space comes from the supremum norm, right? This is a norm on the vector space, right? Because if our function f is in C of AB, then it's bounded, and then this theorem applies. And this is rules for a norm. Okay. So this is really just, this really isn't anything special, right? This is just taking the properties of continuous functions and rephrasing it, in a sense. But now we want to state something even further. And that is that C of AB is a Banach space, right? So we have to get to what a Banach space is. So first, we're going to define, let f sub n, f, let f sub n be a family of functions from some domain to R, and f be some other function from D to R. Then we say that f sub n converges to f uniformly. So this is these two parts are part of the definition. If the sequence of real numbers, I guess I should specify that these are bounded for this to make sense. If the subnorm of the difference f sub n minus f, this is a sequence of real numbers if this converges to 0. Okay. Now our first theorem is that if our family of f sub n's is coming from a space of continuous functions, and f sub n converges to f uniformly, then f is also continuous. Okay. So to prove, right, what we have to prove is that f is continuous. So this means that f is continuous at each point, right? So let's start with a point in the domain. And then we also start with some epsilon greater than 0. Now we can use the convergence here, right? There is some natural number n such that the supremum norm of f sub big N minus f is less than epsilon over 3. Okay. This is the subnorm. Now f sub n is continuous So there is delta greater than 0, such that for any x prime which is in D and also within delta of x, so I have to write it like this. So this is saying it's in our domain and it's also within delta of x. The difference between f sub n of x prime and the f sub n of x is less than epsilon over 3, right? This is using continuity of f sub n. Since now x and x prime are in our domain, and big F sub n minus f sub norm is less than epsilon over 3. So in particular, if I take any value of f sub n minus f, the functional value, the absolute value of that will be less than epsilon over 3. So I can apply that at x, right? So absolute value of f sub n of x minus f of x, this will be less than epsilon over 3. And I can also apply it to x prime minus f of x prime. It's less than epsilon over 3. And now we can use the triangle inequality 3 times, or I guess 2 times, to show that the absolute value of the difference of f of x and f of x prime is less than or equal to the sum f of x minus fn of x plus fn of x minus fn of x prime plus fn of x prime minus f of x prime. And each of these pieces are less than epsilon over 3, so this whole thing is less than epsilon. And this shows that thus f is continuous at x. Because epsilon was arbitrary, we showed that there is some delta such that for any x prime, which is in our domain, and delta from x, the difference between f of x and f of x prime is less than epsilon. And that concludes the theorem. Now we are ready to prove the next thing, which is that C of AB is a Banach space. So I guess first, as a reminder, a sequence is Cauchy, I believe is the pronunciation, Cauchy, if for any epsilon greater than 0, there is some n natural numbers, such that for any m and n greater than or equal to n, the distance between x sub n and x sub m is less than epsilon. And remember that when we defined the real numbers, we defined it to be a complete Archimedean ordered field, right? The completeness axiom was what set the real numbers aside from, say, the rational numbers, right? The rational numbers are also an Archimedean ordered field, but it doesn't it isn't complete, right? There are Cauchy sequences that don't converge. And so a Banach space is a normed vector space which is complete with respect to its norm, right? In other words, instead of this absolute value here, right, this absolute value is essentially the norm for the real numbers, right? So the real numbers, in fact, form a Banach space because the real numbers are a one-dimensional vector space, and then the norm is given by the absolute value. We are going to show that C of AB is also a Banach space. We've shown it's a normed vector space, and now we have to show that it is complete, meaning that if I have a Cauchy sequence, it has to converge it converges to some value in C of AB, right? So, right, that's our theorem. C of AB is complete. And so essentially, oh, I didn't realize I don't have that much space. Let me take this and bring it to the next page, then. Where did it go? Okay. Okay. So C of AB is complete. The proof. So let f sub n be a Cauchy sequence in our space, right? C of AB. And let epsilon be greater than 0. So we have to show that there is some function in C of AB such that the f sub n converge to f. Right. Okay. So using the fact that this is Cauchy, right? There is some natural number such that for m and n greater than or equal to n, the supreme norm of f sub n minus f sub m is less than epsilon over 2, right? Now for x in AB, the value of f sub n minus f sub m at x is, by definition, less than or equal to this supremum norm, so which is less than epsilon over 2. Therefore, f sub n of x is Cauchy in R, right? And thus has a limit because R is complete. So let we're going to let f of x equal to this limit. So we are defining a function, f, such that its value is the limit of the sequence f sub n of x. Now we have to show that this function is continuous and that our sequence converges to it. Now since f sub n of x minus f sub m of x is less than epsilon over 2, we can take m to infinity while leaving n fixed to get f sub n of x minus f of x is less than or equal to epsilon over 2, right? So when we take this limit, and we replace f sub m of x by f of x, we have to include the possibility that we essentially step outside of this boundary. And a way of thinking this is you can essentially rewrite this inequality such that you can say that f sub m of x is contained in some open interval, and then when you take the limit, then f of x is going to be contained in the closure of that open interval, which then gives you this this non-strict inequality. This holds for all x in our domain, which is AB. So epsilon over 2 is an upper bound for the set of values of the difference between f sub n and f, and therefore the sup-norm is less than or equal to this upper bound, and this is less than epsilon. Thus, we can see that f sub n minus f supreme is going to converge as a sequence of real numbers to 0. By definition, right? We have shown that for some epsilon greater than 0, there's an n big enough such that for all n little n bigger than that big N, that this value is less than epsilon. And of course, we know that this is greater than or equal to 0, right? So f sub n converges to f uniformly by definition, right? This is our definition of f sub n converging to f uniformly, was that the supremum of this difference is going to converge to 0. In the previous theorem, though, we showed that if the f sub n are continuous, then f is also continuous. So by previous theorem, f is in C of AB. So we are done, right? We have shown that there is a continuous function that f sub n converges to, and therefore C of AB is complete. And that concludes the lecture. Yeah, so in the next lecture, we will be shifting gears to integration, which may sound weird to you that we are covering integration before the derivative, because most calculus courses, right, cover the derivative first. But this is just the path which the book that I'm following takes, and so I'm not going to stray from that. Anyway, I'll see you then.